Hello, everyone. Good Friday afternoon. So I'm pleased to welcome Robert Dzur, or how I pronounce it, Robert Dzur, to CGM, to the forum. I will read his bio. Maybe I don't think you necessarily read it. It is what we send out. I think it's very interesting, so I still want to go through that. Robert is a senior vice president and system manager of spatial data at Bohannan, Huston, where he, for the last 20 years, he has led a variety of GIS, remote sensing, photogrammetric, and LiDAR mapping projects. His current professional interests include high precision geospatial dataset development, historical mapping projects, and open source technologies. And he is proficient in commercial and open source GIS environments, such as GRASS GIS, Spatial, and Entwine. And I know Robert mostly as GRASS GIS power user, which he definitely is. And then Rob did undergraduate work in Spanish at the University of Arkansas, which I pronounce Arkansas.
Arkansas in español.
Right. Where he also completed his MA in geography. Before joining Bohannan Huston, he worked at Center for Advanced Spatial Technologies at the University of Arkansas, and then he spent 4 years in Bolivia as an international technical consultant for the World Bank, managing cadastral mapping projects. And there is much more to Rob's story, as I always learned when I meet him. So it's good to have you.
Thank you, Waszek. Thanks for coming. I see a lot of laptops here. What we're going to do today is going to be completely interactive. I talked with John about, we might need to get people set up. So I don't know where folks are in terms of the environment that I planned on doing. Does everybody have a working Conda environment on their machine? Maybe not. If not, you can follow the instructions if you download the repo. And so if you haven't been that far, you can go to the repository where the workshop is. I'm going to go ahead and do this on my Mac here. And what I usually do is just download the zip. All right. And this will contain everything that you need to run the workshop material. It may take a little while. It's not a very big repository. About the largest content is the named imagery. And so let me see. This is going to go to my downloads folder. So it's still downloading. And what I typically do, any Mac users, few of you, I see what I typically do, at least on the Mac, is once this downloads, I move it over to my documents folder. As Waszek said, he learned something new about me. I'm an old school computer user. So when I did my undergrad and master's, that was before the days of Windows. This was before Windows 95, Windows 98. So what we had as computing resources were Unix workstations. And so this is kind of never changed for me on the Mac. It's really Linux/Unix type operating system. So, but as I told at the lunch of the day, every day is a great day to be involved in geospatial. I think that we are advancing the field, and I'm super excited about the direction that we're headed with technology. So let's see if so it's finished on my machine. And so I basically will copy this to my documents folder. And then you should be able to open it. And then there's a getting started. PDF that may be helpful to bring up. And so if you open up, at least on the Mac, there's a table of contents where you can kind of go through and have quick access to the different operating systems. If you are on a Windows machine, this I've remoted into a training machine back in Albuquerque. So this is not a very well equipped in terms of computing resources, but it gets the job done. So if you have downloaded the zip file, you just unzip it, and then what I typically do on the Windows side is just put it in the CTemp. At least that's how I kind of prepared the document. I think I might have to restart this because I let it go to sleep while we were doing the intro. Hopefully. Let's see if that's. Oh. Start with VPN, maybe see that. Yeah, I lost my VPN connection there from an activity. So now we should be able to get back to that machine. Okay, now I'm back. So basically put that in the temp folder on Windows, and it has the entire contents of the repository, and then you can, you know, and if you've got Anaconda installed, you should be able to just bring that up from the start menu. And so you can just type Anaconda, I think. And there it is. I typically run it as administrator. That's more of a security issue at my company, but that should get you the Anaconda prompt installed. There are some particulars for Windows that I kind of cover here. This will take you just to getting started at the Anaconda site for downloading and installing. Then we're right here on Windows. Start your Anaconda environment. You can also, because I use Git to move data, I installed Git with Conda install Anaconda Git. So this I've already done in my Anaconda environment. It's often, even if you do a fresh install of Anaconda on Windows, it's useful to go ahead and update the base. And so I recommend kind of going through that next step. And then also, if you are pulling from channels, it's good to add the Conda Forge channel. You don't necessarily have to do that because I've created what's called a YAML environment file that's part of the repo that takes care of that, specifies the channel. But that's all this in the setup on Windows. So I've kind of done that, and that's where we are here on the Windows side. So one thing to note on Windows about this environment that you don't have to worry about on Mac. Mac, you can follow the instructions. There are some caveats because I kind of developed this YAML file to work more on Windows, thinking that's what majority of people would need. One thing that's particular about what we're going to do is that you kind of, if you have a GPU on your system, that's going to be better. I set it up so that it'll even work if you don't have a GPU, if you're CPU only. The caveat to that is things may take longer to run. So just be advised about that. This next section too, there are some additional aspects about the CPU, GPU thing. So you need to kind of know you have to, on Windows, unfortunately, for Ultralytics to work. Ultralytics is the makers of the YOLO modeling, open source software. And so that relies on PyTorch. So you need to downgrade the PyTorch to a previous version on Windows. And so that's what this next step talks about. And so I'll go back to, so if we, I'll CD, I'm already there, but I'm going to CD to the temp folder. So try to do that. Now I'm there already. Let's just do a DIR here. So, so we can run NVIDIA -SMI to check if you have an NVIDIA card. If you do have an NVIDIA card, it will display these settings. You can also look at the task manager. If you have a discrete GPU, you should see that like I have here on this machine. So you'll see GPU 0. So that's the integrated Intel display device that's on this machine. But we also have a discrete GPU that's GPU 1, and that's the NVIDIA Quadra P1000. And then over the output here tells us what CUDA version we're on. So that's kind of important. Most of the modern Windows machines, if you're running NVIDIA, will have probably a similar version of CUDA. If you're running an older version of CUDA, that may be more complicated. You need to go back in time. You can install older versions. You just have to edit the requirements file. So let me just show you while we're on the Windows machine here. We have a YAML. So I'm going to open this with, I mentioned Visual Studio Code is kind of my preferred environment. We'll run most everything. When it comes to the notebooks, you can launch Jupyter Notebooks and run through the browser, but there's a lot of extensions with Visual Studio Code that I think are beneficial. Probably my favorite is a spell checker. So you can add a spell check and be able to spell check your Jupyter Notebooks. And I think that's, to me, probably the biggest benefit. But there's some widgets too that you'll see as we run these that I think are handy. You get like a dynamic process counter and some other things that I'll point out that I really like. So there's a couple on the Mac side. We'll go into this file and we will comment out the M2 baseline. And then we'll also comment out the requirements file, because the requirements file is where we're specifying the versions of PyTorch that we want. So let's open up the requirements file.
Can you please zoom in the VS Code?
I mean, change my resolution here.
Yeah, just make
it bigger, or
I guess.
I don't know if I
I
can.
think you should
Control and the wheel. I don't know if you're.
I don't have a wheel, but I see.
Two fingers, something like
You
that.
can figure spread.
Or Control plus, or whatever control is on that. Or, okay, oh, you are on the back, which is connected.
I'm connected to Windows. Okay, I found it. Control plus. Did that work? Okay. You still with me?
Yeah.
All right. So as I mentioned, when we're on the Mac, we're going to open this and we're going to comment out this M2 base line, because we don't need that. And then we're going to comment out this requirements file. I just opened the requirements file. Let's see. To make that a little bigger. So as I mentioned, the requirements file is by default set to CPU. So you just need to, and I think in VS Code, you can comment the whole line just by doing control and then /. On the Mac, it's command /. So here, because I have a GPU and I have version 12 of CUDA running, I'm going to uncomment the second line for that. And then this is just telling Conda to build the environment, including PyTorch, grabbing from that URL and then installing these previous versions. Current version of PyTorch is 2.4, but this will work great on Windows with the 2.3 versions. So then you just want to save the requirements file if you have a GPU, and you can get out of that, and then we don't need the YAML as well. So let me minimize that, and we'll. So with that done on the Windows machine, we can go back and look at the instructions. So this is all we did here was comment the CPU, uncomment the GPU version. Now we're ready to create the environment. So you should be able to, and this is a little tricky. I'll see if I can copy from Mac and paste to Albuquerque. That sometimes doesn't work. So you'll do a conda env create. So I'll just do that here, conda env create, and then from file. So that's -- file, and then it's environment. .yaml. And you can tab to autocomplete that if you want. So this now will start to build.
Oh, you missed an E in create.
Oh, gracias. All right, now let's try it. And then if it starts up and it's saying, hey, we're gathering the dependencies and whatnot, that's a good sign. On Windows, this may take a while, so let's go back to my Mac side. Here on Mac, we should have that here in the repos. So I'm going to open the environment file here. And again, let's see if I can, here on Command Plus to increase the font there. So M2 base, that's a library that allows Windows to have Unix, Linux-like functionality. So you'll get the ls command, the cat command, all kinds of GNU type utilities. And so a lot of that's built in on Mac. So there's not that library doesn't exist for the Mac architecture. So your build would die because it'll say, hey, you can't find this. Well, nobody is using that on Mac. So we have to comment that out. And then likewise, we'll comment that requirements file because we don't need to downgrade the PyTorch versions for Ultralytics to work. So then that's all we need to do
Can
here.
you zoom also a few points in your, well, in the next file?
This one?
Some too maybe, but yeah. I'll complain again.
No, help me out there, Vacek, that's good. Okay, so we can go down to, the Mac instructions and build the environment. And so we've downloaded it. We are, there's some things, sometimes building an environment on the Mac side, if you don't own, and I've run into this on my Mac, where root is the owner of the .conda file where the environments get written in your home directory in your profile. This will resolve that if you get an error. So I usually, and I change this to our Dzur, which is my account, to take ownership. And then we did the commenting for Mac. And then now we're ready. I should be able to copy this line and I don't know, can I increase my font here on this? This just seems to make
You're
that
from the view.
bigger. Oh, from view. Bigger it. That's not a lot bigger, is
Very,
it?
very small increment.
Yeah. But essentially, I'm gonna put this command here, and so this is. I need to change directories first to where we put the repo. So now we should be able to do that. Okay, so now we're kind of catching up on Mac with what Windows is doing. Windows, as I mentioned, is a fairly under-resourced machine here. It's doing the work. It has, it's for, I don't know if I mentioned this, but I'm at an engineering firm. So most of the time, these computers are built with AutoCAD. They're not doing a lot of heavy lift. So they're really good for AutoCAD. This is just our website. And what we do is we support all the engineering infrastructure. Just a quick comment on that. We've got 250 folks in our company between our headquarters in Albuquerque, an office in Denver, and one in Las Cruces. And we're primarily dedicated to building infrastructure, like you see, home sites. We do bridge work, highway infrastructure. We have a water group that does water modeling, and you can kind of tell from these are actual project sites that we've designed. Every one is on the landscape, and so for the engineers to be able to do their work, they need to have existing conditions of what's there before they can do design. This is actually a proposed design on the other side of the mountain, the Sandia Mountains there in Albuquerque, where we redesigned the roundabout. And this is working in Unreal Engine, which is the Epic Games environment, and you can bring in actual real terrain data. And so that's what this was built on. And my group did the mapping for this particular project. And then this is what we're doing these days, just from a public meeting type standpoint, to communicate to the public, hey, this is what the redesign will work or look like. With Unreal Engine, you can kind of create a real gaming type look and feel that changes, the lighting, the time of day. And so this is just another project. And that's all this does, is loop through videos of our projects. So let's see if we're done. So now we're doing the PIP dependencies. So the first dependencies in the YAML are fetching those dependencies from Conda, and then in the YAML you saw some PIP entries. Now it's doing the PIP installs here. Let's go back to, so on the Mac, I'm done. So we can go ahead and activate this. So we're gonna kind of activate, and then here we'll just kind of go through that. We'll check our environment just to make sure things are working. So the first check that I have for us is to go into Python, and then what we're going to do in these notebooks that I prepared is we're going to do the model prediction and inference steps, but there's some data prep that we need to do before that. So we use the Relief Visualization Toolbox. There's a link for the references on that. That's a Python library that got installed, and so this first one is just checking if we have that library correctly. So we'll import RVT, default. And then that'll function just as if when we're in the notebooks, we're running the same command. But here we're just doing it interactively. So that's a good sign if you get that far and you get no issues on the import. And then we can do the same thing with Ultralytics. Hopefully, again, my deficiency is spell checking, so hopefully I got that correct. And then on the Windows instructions, I also put the YOLO checks. So we can go back here to build the environment and check the environment. So I did the same. We do the same things on the Windows side. Because we have the issue of the CPU, GPU on the Windows machine, these machines, I'm on an M1 Silicon based Mac, vintage 2021, so about 3 years old. But the M1 has integrated GPUs on the chip, and so those we don't really have much choice. It's what Apple provides in terms of GPU. But I think it's still a good idea to do YOLO checks just so you can see. So we'll exit out of the Python environment and then we'll run YOLO checks here. And so this is a good sign for Ultralytics, and it tells you the libraries that we have installed. You can see here we've got PyTorch libraries that are 241. So that's the only difference between what we're doing on Windows to Mac in terms of library. We don't have any CUDA. So on the CUDA entry, it's going to always say none. But we do have our Apple One Macs recognized. And then I'll show you when we get to it in one of the notebooks, how to do the check for the GPU. And this machine has 10 CPUs, 64 gig of RAM. So pretty good machine.
Does the library work with AMD GPUs as well?
I'm not sure. We have a machine with AMD, but we haven't tested the AMD's GPUs. You might have to go to PyTorch's website, and I put a link to that and see if they list. I'm not sure that they do though. We've had some spotty luck with the AMD GPUs. We've got a 2019 Mac Pro that came with 3 high-end AMD GPUs that never really, not for this, didn't really deploy it on this, but never really functioned quite like we hoped. And they were expensive too. So that's sometimes you buy stuff. In fact, that was one of the whole reasons that I did these notebooks, because we had a 2018 Linux machine that we were trying to replace. And we were getting some feedback, hey, you know what you really need? You know what the performance is of what you have? How are your Macs doing? Could your Macs do this work? So I grabbed all of these North Carolina data sets this summer and created a hardware check against 8 different machines, including many different Macs, Studios, different M1, M2. I even did an M3 on a MacBook Air. And at the last minute, we said, all right, let's throw in our old Linux machine that we want to replace. And on the GDAL image splitting or quartering task, it was the best of all machines. And we benchmarked that against a Windows machine that was for our visualization group. A lot of those visualizations, they need heavy GPU machines. They paid $18,000 for that machine, and the 2018 Linux machine that's a 2.4 gigahertz processor, I think, killed it and beat it. And so So lesson learned, you may not want to throw out the hardware that you think is aged and decrepit. We still are, obviously, and you'll see, GPU is required, so that machine had a weak GPU, so we still need to invest, and a lot of that cost is in NVIDIA GPUs. So, and it's working well for the visualization group, but yeah, I don't know, man, sorry about the diatribe on the AMD there.
That's okay, plenty of information there.
Yeah. So now,
So, sorry, from the people who want to follow, is there someone who wants to follow and doesn't work for them? It's also fine if you want to just like look at it, but if you want to actually do it
Yeah,
yourself and it doesn't work,
because I think at this
raise your
point,
hand, I guess.
yeah, we can help out. How are we doing on the Mac side? Are Mac folks with a Conda environment and have tested it and ready to go into the notebooks?
I'm not ready to find.
Well, where are you at? We can.
My environment's still doing that as well.
Yeah.
Yeah, you probably have everything cached to download it, right? So
Yeah.
for you, it's only installing, not necessarily downloading.
Yeah, on this machine, I think it was downloading everything.
There's like conflict on make an environment and clear the terminal look like there's a conflict between like package and dependencies. But in Conda, and all of them like if I can make this environment in Conda Forge. It makes sense. Basically. Do this, or like should I make it a default?
Most of the YAML is pulling it from on the Forge, I think, so you have defaults as well, there. Did you try running, the YAML?
Yeah, I did,
And that told you there was a conflict?
there's a conflict, but it was taking forever, so I just canceled it and like.
Good, try the YAML without the defaults, maybe edit that. And sometimes, changing the order to, the sources. Maybe I'll give a little bit more time on the wheels that'll keep turning. And maybe we just briefly comment, on, what we're going to run through next. So, this is the repo. I have a little bit of an abstract that tells you about, what we're planning to run. When I talked with John initially, he said, hey, we're gonna get together. These folks in these forums are typically looking at exploring the frontiers of geospatial. And so I kind of reflected on, okay, what are we doing today in our business that's at the frontier of geospatial? I think really in this first one, I selected the AI craze really hit the media last year with ChatGPT. Which came out about 2 years ago, I think came out 2022, their first commercial release. And we have been years hearing in the engineering industry, what are you doing to prepare for AI? We weren't really doing anything. And then 2023 hit the media, and in particular, we started seeing OpenAI and what they could do with, just creating imagery out of nothing, out of prompts. And so we thought we've got to take this a little more seriously. And that's when we started looking at the YOLO tools and doing object detection is kind of where its sweet spot is. And for us, the model that we're going to run is a building detection model that we created last year. We're a data producer. We make elevation data, image data, and feature data. By feature data, I mean lines, points, and areas that engineers can use in a CAD workspace or a GIS environment. And so we want that to be the very best quality. And one of the hard things for us as a LiDAR producer is engineers need a ground surface. Well, by definition, a ground surface shouldn't have buildings left over in it. But if you're working on thousands of square miles, that can be daunting to review manually, find that last mile, that last building. And so we thought, well, what if we could train an AI model to detect leftover buildings in our ground surface? And so that was the genesis of this first one. And we still use that model. We ran it on data in the Southwest. So it was new for us this summer to say, hey, I wonder, and I've picked the North Carolina data that you have, it's statewide data, because it is very good data. Even though it was produced in 2015, they classified buildings in those data sets. And so if you classify buildings, that is something you are paying attention to. And so I found the data to be very clean from that standpoint. And so we ran it on the entire phase 3 data set. We actually ran it, and I mentioned down here, we ran it on phase 2, phase 3, and phase 4, which is in 2 different years, 2016, 2017, and found all of those to be very good. Actually, phase 3, where Raleigh was the best in terms of the quality. We also found some things about our model that we learned and need to improve our model on. Not probably going to get into that much, but just to kind of show you how the model works. Because the other common thread to all these things that we develop is they're all LiDAR based. So the source data for our model are DEMs that come from a LiDAR source. I thought, we are awash in point clouds of different character, and I kind of put some links here. These are our point clouds served off of our Entwine server, so you're welcome to hit those. But they show you the gamut from large scale aerial collected LiDAR, mid-scale aerial collected LiDAR. We have mobile LiDAR projects. We have terrestrial LiDAR, and we are also doing UAS LiDAR. And I think the future for us is we have lots of surveyors that are out in the field, and standard equipment right now is a total station that has LiDAR on it, it's a LiDAR scanner. And so the terrestrial scanning is a church in Mesilla Valley, or Mesilla, New Mexico, near Las Cruces, and that's for high accuracy forensic surveys. And so I think, and we right now only have one aerial drone LiDAR sensor, but I think it's just the beginning of the surveyors are going to be equipped with LiDAR units in every truck. They already have them in the total stations, and they're going to be flying. And most of our field crews are all UAS drone certified pilots. So the forefront geospatial, if a survey crew wants to work for us and they aren't wanting to be a LiDAR or a drone pilot, that's going to limit their options, or whether we even have that as the job requirements going forward and hire those folks. The only thing that I haven't put on here that we really haven't done a project on, but how many of you have an iPhone? So are you 12 Pro and above maybe? Okay, well, you have a LiDAR unit on your phone. And about the only thing I've done with my iPhone is scan a deep dish pizza and say, wow, that's cool, but this technology has been embedded on the iPhone for a number of years. And I'm seeing articles in journals where forestry schools are talking, and there's an acronym for this as well that I've seen. It's called personal LiDAR scanning, PLS. And so you might see that in the literature here going forward. I'm already seeing forestry schools saying, hey, can we use these PLS devices to measure DBS or DBH, diameter breast height, in the forestry application. So the LiDAR is here to stay. And I think the issue is, how do we make sense of it? How do we consume it, which is really the content of the second one. And then the third one is, how do we create meaning? So that's the GRASS GIS piece. Our engineers don't want to consume lots of point cloud data. It's too heavy. But they still want the benefit of the resolution. They still want the derivative products. And so we rely heavily on GRASS to really create that meaning out of the point cloud and turn data into information for them. Where does the water flow? Where are the patches of vegetation? So that's, I think, the next step. And also, even though GRASS has more than 30 years, I think GRASS is part of our future. And I think, you know, the other thing that's powerful to me, and I put that here, if we open up the Entwine, I think I already have a link to it. So this is a cool site. Howard Butler's put this together. It shows all the 3D projects that are out there. You can, and you'll notice that each project, you zoom into this map and see a project of interest, but you can also find the list here, and he lists how many points are in the project, and they've got a poetry and an Entwine instance. And so the notebook that makes Entwine is really this format. And you can view it, and that's really great for an engineer that maybe doesn't want to deal with the points, but wants to see the fidelity of the point cloud. They can view it through, the only software they need is the browser, a WebGL enabled browser. So we found that technology to be hugely important just from visualization and data access. All right, how are we doing? The wheel's still turning? Oh, man. So I was afraid of that.
Oh, no, my wheel's done. Sorry.
All right. All right, Dell. It's been a decent machine. Let's see, Huston. So go ahead and maybe get started on the notebooks. All right, well, if your wheels ever do finish, just know that the repo's there, it's not going away. Or maybe try it on a desktop that you might have more power. So, all right, let's get going here on the notebooks themselves. So I'm going to start off with the first notebook, and that is the Get the Data notebook. Okay. So the data that we're going to work with, I already mentioned, is the is that a look on the station? A little bit more. So I put the links to the statewide data at the NOAA site. You can check that out. So for like, I don't know if this will bring up the NOAA site. So there's the DDMs. You'll notice that even NOAA gives some advice about how to retrieve the data from their site. So you can wget, and they mention that here. I initially designed everything on the Mac with wget in mind. You can install wget and then use it exactly like they specify, or as I have specified in the notebook. On Windows, wget isn't available. So we emulated wget here on Windows. And so we Pythonized wget into a Python command, basically. So the first thing to do, is load my kernel here. So I'm going to, use the NCSU workshop, kernel that we just created. And so, that gets loaded. And then once you have that loaded, you can, I usually do a control enter on the Mac, but you can use the play button to load the. How are we doing, Doug? You there?
Well, I started with the notebook, but do I need to load something before that or what? Oh, wait, I see it.
And can you maximize it and maximize the window and make it bigger, make the font bigger?
Let's see. How's that? So there should be a kernel.
Kernel doc now?
Also, in the getting started document, there's a. You may also, if you haven't run anything in Visual Code before, you may also want to, and you can check this in the Visual Code instructions. And actually, I probably didn't follow my guidance here, but we should probably open the folder. Let me go back and do that. So I can save that. So this is the open folder. And then I can, it's already there, so I'm just gonna open the folder. That might minimize my real estate here since I'm so zoomed in, but basically that opens up a tree here that is handy for accessing the notebooks, the folders, everything that we create. All right. And then, so now we'll go back to, I'm just going to scroll down here on the sidebar. And here we are with I'll go back to the top. And since I already selected the kernel, I think it recognizes automatically that I need to be in the NCSU workshop environment. Let me go back to the top. I'm going to minimize that a little bit. Okay, so now that we have the kernel selected, we can run the first cell. And that loads all the environment, just like we were doing previously. The next cells, I typically, since I'm an old school bash guy, I like to know, okay, what's my current working directory? So these are just doing that. On Windows, this should work because we've installed the M2 base, so you should be fine. These are just different instances of the same thing. There's the Python, and then this, if I run it here, it's not really going to give me anything meaningful, but on Windows, that would give you the current directory. Okay. And then this next one is just going to emulate the wget functionality. You'll see that I have the wget code in that bottom cell. There's a commented out code line. That's wget. You uncomment that. That'll still work on the Mac, but the Pythonized emulated version will still work and download the data. And so that just defined the function for this get URL list. And then we can execute that. This is for the what I call the original product resolution, or the OPR, which are the DEMs. So that went to the links that I gave at the top, where Noah says, hey, here's our list of files you can download from, and if you get that for the phase 3 data, that is 11,000 some odd URLs to 11,000 tiles. So But we got the whole list, all right? And then we'll do the same thing for the LiDAR point cloud. We'll download that list. In the repo, I provided a subset of, in fact, that's in this reference folder. And we can, this is the CSV that we're just gonna say, hey, use the cat command to print the contents of that. Just again, more feedback. Here's what we have. These are the DEM files that we're gonna download from NOAA. It's only a subset of 30. And then once we've kind of, okay, my CSVs are good. Let's parse the 11,000 URLs against this CSV. So basically what this next function does, it makes a filter the URLs function that we're gonna run. So this defines that, and then we follow that up. Before I had a bash statement that just said, hey, I got this CPU or this CSV of 30 files. That's a bash for loop that says, okay, for every entry in the DEM list, give me the corresponding URL from the broader 11,000. So we're doing the same thing, but we're just doing it with this Python function. And then I've got some feedback here in the function that tells you, okay, we've downloaded those 30 URLs. So what do I do next? Well, if you're me, you want to say, all right, is it gibberish or is it real? And so this is just more visual feedback with the cat command again to say, yeah, those look like, and they point to Amazon. So we have some confidence that this will work. All right, so next, I've got 30 URLs for the 30 files that we want. This table is just showing you the benefit of multiprocessing. So this machine has 10 cores on it. We don't want to just use one. We can just use one. If you just do a wget command, it's going to, in serial mode, download one at a time. That's what I have here as the first two entries. And so for the 30 files, when I ran this, it took 2 minutes to download the DEMs and 18 minutes to download the LiDAR point cloud or the LPC files. So I've commented that out. If you're on Mac, you can try it yourself. But we're going to skip over that, and then we're going to run it with the multiprocess library. So the only thing that this cell does is says, hey, where are your links files? Where's the input, and where are you going to put the data? Before I do that, let me go back to the instructions. And one thing going forward that's useful. Because I have a lot of empty folders on GitHub, it's important to delete the git ignore or the hidden files. And so this just gives you a directory listing if you're in the repo and finds hidden files that are called git ignore. And then the next command is a for loop in Windows to delete those files. I also have that down here in the Mac instructions. And so I'm going to run this. This is doing the same thing that is above in the Windows instructions. So here we're just using the find command, and we can see that we have in these empty folders that got downloaded, GitHub, for them to be uploaded, needs something in them. So this is just placeholder. But I am going to remove those with this for loop. And so we're going to paste that in here. And now if I rerun my find, those are cleared out. So that's not necessarily important for the first notebook. But when we go and do multiprocessing and give a list of files files, if we have an extra file that's a hidden file in there, that can mess up the processing and where things are located. So just wanted to point that out as well. All right, so let's define the input output for the download of the DEMs. And then let's go ahead and run that here. And let's see if we're close to 10 seconds over the guest Wi-Fi.
You make it just a little bit bigger.
Sure.
You should just record that.
Yes.
So it looks like here on the web, my
Should be caching.
Wi-Fi may be a little slower. If we're on a network connection, that might make a difference too. So this may be a little bit slower.
It's actually working pretty good.
Are you doing all right? And, you know, the benefit here is we're using the full bandwidth for the full amount of processors here. If we were just doing this one file at a time and then getting the next file, this would be much slower. We can queue up the next step, which is the LPCs. So when that finishes, we can work ahead. You can see there's a clock here. This is gonna, in VS Code, it's gonna work in serial mode. But now you can see that that process above finished. That's what I like about, I was saying there's little widgets in VS Code that maybe you don't necessarily get if you're running Jupyter Notebooks from a browser. And then we can do, so we set the input output there, and then we can do the same thing. We can run this code line. This is much bigger point cloud data versus the DEMs. So that may take a little bit longer. And if we go here now, you can see that we have data populated. We should have 30. It does look like we've got quite a few there in the OPR folder. If I go up, likewise, if you open that initially, there'd be no contents. Now that we have the download working, we're starting to get the data populated here. So that'll be all of the data that we need to grab. I do have some other exercises at the end of this for grabbing NAIP data. I'm not sure we'll want to go through that given the Wi-Fi, but these are additional means to get NAIP. And these sites are current NAIP. So that's another issue. The LiDAR data is vintage 2015. So that's why I packaged 2014 imagery to kind of give us the similar temporal range. It's a very interesting comparison. If you get current LiDAR for the exercise that we'll do, you'll see, even though it's very rural, the landscape's changing between current NAIP data sets and historic NAIP data sets. So let's see how my process is doing. So yeah, I don't know, this Wi-Fi may be taking a little longer. I can let that run. I might, because the next step is only dependent on the OPR. So we can, I'm gonna zoom a little bit back out. Apologies, I'll check. Let me.
It, like the whole interface zooms, right? So you kind
Yeah.
of lose space there.
Yeah,
I can test if I can.
it's
Or you
hard.
can close the side panel and then you would have.
Yeah, I could close the slide,
Closing it and opening it, then you.
or I could just go back to the window here, and I could open the data Yeah, I can close the side panel. That maybe is better. But here I want to keep the side panel open so that we can go to the number 2 notebook. So, and then let me close that again. All right. And so this next step, we'll let the LiDAR download. And let me zoom this in a little bit more. So now we're getting into the actual model aspect. So Skyview factor or SVF imagery is what the model was built on. It's what the model was trained on. We did not initially come to that as a good model for this application. And I'll show you in a minute what we typically work with to review DEMs is shaded relief, standard grayscale shaded relief from one direction. We use the GDAL standard, which I think is 45 degrees at 315 azimuth. And that works great. We're used to it. We thought as humans that, oh, man, AI is going to eat this up. Well, the AI will do a great job. It did as we but it made a lot of mistakes too. And I think part of the problem that we learned was that traditional shaded relief is unidirectional in terms of illumination. The advantage of SVT is that's multi-direction. So in this case, we're using the defaults. So that gives us a 16 directional analysis. And the default also is to go out 10 pixels. And then those pixels are, if you're not familiar with Skyview, are differentially shaded in the composite image of those 16 directions to look at how open to the sky, thus the name, how much sky can you view from every pixel. And so if you're standing in the middle of a field or a roadway, you have a 360 view to the sky. And so that's going to appear white in the image. And then if you are in a hollow or a ravine, you are blocked to one side maybe, that'll appear dark. And so once we introduced Skyview factor to the training, the models boosted performance in terms of confidence of inference by about 20 percentage points. So the model that we have currently, I would say, is in the 75% range. So we weren't doing great, I don't think, at just above 50% with single shaded relief. So that was a big takeaway for us in this exercise. Let me go ahead and I have the kernel loaded in this. So this one, we're just going to load the libraries, the RVT libraries principally here. And then, as is my routine, hey, where am I at? We're in the NCU workshop main. Once again, we're going to define the OPR folder where the data downloaded, the DEMs, and then we have a Skyview factor folder here. So I'm going to run that. That's just a definition. And then these are the references for more details on the RVT toolbox, which is a Python library. And now we're going to start to do for each of the 30 files. And there's a GDAL warning here, but it's trivial. So that just made 30 Skyview factor images that are multi-directional and go out 10 pixels in 4 seconds. This is, I think, the real payback in terms of time savings. 4 seconds, okay, we could have done this in serial mode, but if we want to do it on all 11,000 images, then we're looking at more time investment. And so that's where the power of the multi-processing really comes to bear.
Does that have an issue with Edge?
If you can do Skyview factor on a DSM, And that's, I think.
No, I mean
also-
about the edge of the third
Oh,
mile.
yeah, it does, and that's what I was referring to. We need, and it depends on the project, the producer, and so we could do something, I think, to mitigate edge effect that would improve our model, or conversely, we could add more training to tell the AI model, this is not an issue when you encounter something and so running this and finding false positives like that on edges is valuable to help us identify where we can improve the model. This table shows you kind of the differential on this laptop. So when we did run it, 11,269 DEMs, that took 22 minutes. That's still, for that many images to run that sky view factor analysis is huge time savings for us. And this is, I think, if there's anything to take away from this, if you can, use geospatial processing with this multi-process pool library, I highly recommend that. All right, so that's done. This next one just creates a text listing of those. So, and it dumps it out in our reference folder. Then, once again, I'm using the cat command, make sure that I didn't write out some garbage. You can see that we have SVF file listings there. Then I'm going to make an index. So this is a vector file with GDAL, just to give us an index. I'm also going to use the text file to create a virtual raster format. And then I'm going to use that and I'm going to GDAL warp that into a hard tip. We found too, when we've applied other analyses, DRTs add overhead to finding where the source tile is. And it's much more efficient to use a hard TIFF often. So that's it for number 2. I'm going to save that. Let's see. So my LiDAR data is still downloading, so we'll let that go. Let me fire up an instance of QGIS. I'm going to open fetch in applications, QGIS. And I'll just show you what the sky view factor image looks like. Okay, so I'll just go to the reference folder. And here's the sky view factor tip that we just made, and we can load that in. And you can already see kind of the differential shading where we've got 2 main drains that are dark here. So in those drains, you're not going to have a complete view to the sky. And so that's why you see them as more dark. And then we can zoom in and see just kind of, it's really, I think for me, a little harder to interpret. You can kind of see stuff like this where we probably have a building, a set of buildings, maybe some chicken farms. We've got a pond here, and then you can see the dam right next to the farm that's dark on these pixels. So that's where the lower part of the dam is. We can, if you have, I mentioned plugin, we can bring in Google Hybrid here and kind of give you an idea of what's going on. Keep in mind, we're building this off of a digital elevation model. So those buildings have been removed from the surface. There is some triangulation artifacts that you can kind of see some differential shading on. So they might have to use GRASS, what's the RDOT hydroflatten, and flatten those building footprints maybe. So
All the ponds.
yeah, definitely the ponds also. These are probably ponds that were less than 2 acres. And I think with what you guys have just added as an add-on, that would be a good improvement to this kind of data. All right, so that's what we're prepping to go into the prediction model. Let me go back to, we're gonna run split skyview factor, number 3. All right, so go to the top here. Once again, my model is or my kernel is loaded. So I just run that first one. This is splitting those skyview factors images, which are the same size of the DEM, into 4. Why do we do that? Because when we go to Ultralytics and we train the model, another thing that we've learned is Ultralytics is great for web images, smaller scale images, things maybe that are off your phone. I believe their default in terms of building a model is a 640 pixel. Well, if you've downloaded DEMs before, I don't think I've ever come across lately a DEM that was 640 pixels, whatever resolution it was, by 640 pixels. And so they're more like 1600 pixels. I'm not sure what this one is, but it's much larger than the default. So what we've tried to do to work around that constraint with YOLO is feed YOLO images that our GPU can handle in terms of training. We built this model on a resolution of 1280. So if we quarter these and they're 1600, we still are going to have a high enough resolution to capture the fidelity, in this case, of the objects that we're looking for, buildings. And so that's another thing to think about. You can use these tools for geospatial applications, but they may present other constraints to you in terms of what you want to get out of it. And if you leave the model to the defaults without accounting for that resolution, you may not get predictions that are meaningful because it's downsampled the quality of the image so much that it's not predicting what you expected. So we went through that, and that's why we quarter the images. So again, we're going to use multi-processing, and we define the input output here. And all we're doing is a 2x2 splitting. So kind of like R.tile, you just define the columns and rows that you want to split. And then this folder will populate the splits. So we'll have 120 images now that then, and if you wanted to do training, those would be ready for training, or in this case, we're going to go to the next step, which is we're going to do the inferences. Again, it ran very quickly, 1 second to do the splitting of those 30 images into 100, or those 30 into 120. I think 1.6 when I was running it before. This is the process that I was telling Doug about of the Linux machine we were going to replace. Kicked all the other machines to the curb. And when we ran it on 11,000, it did them in 2 minutes or something. It was just phenomenal. And so it wasn't much faster than the Mac, but twice as fast for that many images can add up. And so that was a lesson learned just in doing the benchmarks. All right, so we're done with number 3. We can go in to look at number 4. So now we're actually going to run the predictions. All right, and just like all the others, here we're going to load the rasterio library is one that's that we'll use. Let me see that. I need to click in there. Okay. And then this is loading the Ultralytics library that's doing the predictions. And then we're going to do the inferences. I'll check the directory first. This, if you're on Windows, you don't have to run this. This is, well, this next one you do, but I talk about the device equals MPS. One thing to note, if you are on Windows, you'll change the device equals MPS to device equals 0. And then that'll go use your CUDA device that you set up in the early instructions when we did the environment creation. This is also other parameters. It tells YOLO where the model is that we're going to do the predictions on. So I have a models folder on the repo. This is our best SVF model that we'll be running. And it's going to use the source that we just created, which is the tiled 2x2 sky view factor data. And then it's going to dump out into a runs folder. So we don't have a runs folder currently, but we'll be making that here. So let's run that. All right, so again, just like the setups, those are quick. This, again, is Mac only, but it just confirms, kind of like what we did with YOLO checks to confirm the CUDA. This confirms that this is just Python code that confirms that you've got a Apple Silicon metal performance shader GPU. Next, we're just going to run the predictions with this next one. And this won't take too long either.
Excuse me, what were you supposed to change the MPS to if you're running? To 0?
Yeah,
Like MPS equals 0 or just 0?
just 0, just device equals, and then instead of MPS, put 0 in there.
Okay. Do I need quotes for that?
I think you may.
Okay.
If you have 2 GPUs or 3 GPUs, it's 0, 1, 2, 3.
Okay.
So we typically are training on a 4 GPU system. But if you only have 1 NVIDIA GPU, change that to 0. So it saved the results to that predict folder, ran the predictions on the 120 quarter tiles in 12 seconds. The next one, basically, it's also capturing details about the predictions. And so we're going to convert those with the next cell to a shapefile that we can load up. And so, and then you'll see that the shapefile will have these attributes of how good does the model think it predicted that, what's the class, and what file did that prediction occur in. So you could go find that file and look at it if you wanted to. So we'll go, this will dump out into this GeoPredictions folder. And now I have a building prediction shapefile. And there we go. So we can zoom to that. And I'm going to change the symbology to be hollow red. And you can say, that looks like it might be buildings left over. Right now, I only have the Google imagery. And so maybe I'm doubting whether or not the model's working or not, because there's no buildings here, but yet it predicted some building. It could be a false positive, like it could be an edge effect or something. But what I would normally do, let me go back and see if we have some results. Okay, so I got all the LAS data. So we can quickly go through and do the same thing we did for the SVFs. We can just generate some text file listings. I'll run those and we'll make an index. I'm going to make a clipper here. And then we're going to make a DEM. And then we're making an image DRT of the NAPE. And then we're going to make a hard file of that. We're going to make a geotiff of our DEM mosaic, the 30 tiles together. And likewise, we're going to do that here for the NAPE data. I'll go ahead and go back to the reference folder where these get dumped. And so there should be, and here it is, there's an OPR folder, that's the DEM mosaic. So I'm just gonna drag that in here. And it may be hard to see there, so, because this is the DEM, just grayscale. But let's go ahead and change that rendering to hillshade. And I like to do bilinear. And okay, maybe now there's a little more believable aspect to the fact that there's predictions here and there's actually buildings. So the issue, the reason we don't see that in the Google imagery, any guesses?
Google imagery is nearer than the DEM data.
Exactly. That has more currency, which is why we want to see if I. See if I. It's below that. So this is the NAPE imagery that we just mosaicked with the first notebook. Why that's not. Looks like I may have some issue here with my NAPE data. Let's see if I can make that again. Okay, I think maybe this QGIS was confused. So yeah, 2014, these buildings were there. And now in current Google imagery, they're removed. But at first, I hadn't bothered to go get LiDAR or image data that was concurrent with the LiDAR data. So I thought, man, what's going on with this with our model? It's not working in North Carolina. There's some problem, but no, it still does predictions, as we can see there. So that's the NAPE imagery. Since I'm on this notebook number 1, I'll just kind of go through this and let it run. So we have current NAPE available through USGS. This, instead of getting it from Google, we can use GDAL info, and that will go look at this national map service and print basically do a GDAL info on it, tell you that it's WGS 84, it'll give you band information. And so we can use GDAL, and that's what we're doing in this next statement. You see there's some XMLs. We're basically going to write that GDAL information into the into some XML files. So we'll run GDAL translate and record that GDAL info information as XML. Once you do that with GDAL, GDAL can run commands like GDAL warp. So what we're going to do with this next GDAL warp is we're going to go retrieve off the national map. And so that repository is the whole country. But in an earlier statement, I did a dissolve where I made an index of the DEMs, 30 DEMs. So it's just a vector tile of where the 30 tiles are. And I had OGR dissolve that, just basically make the union. And so that union vector, I'm telling GDAL warp, hey, go grab NAPE data from this national map web repository. And oh, by the way, do a translation of the coordinate system from lat long to my coordinate system 6543 Carolina State Plain. I want you to make it in 2-foot pixels. I want it to be a cog, use a cut line. We're gonna use the cut line that we made with the OGR dissolve, and we're gonna crop that download and clip it to that polygon. And then we're gonna do compression on it. And that's it. And we're gonna use 70%, 75% of the RAM on the machine and 10 threads, okay? And ignore existing overviews is just, hey, want to add overviews. If there is some, ignore those. So this is working. We're gonna do the same thing for the color infrared. So like I did before, I'm just gonna load that and it'll try to run that when it's able to. So we can go back. We're done with that. Maybe before I go through that, we can actually copy. And if you wanted to see the housekeeping that YOLO does, we can go and I can go in my file explorer and we can paste that. Actually, it's not, it's on the runs predict directory. I'm gonna just make this a little bigger so you can see what's going on. So this is the tile that YOLO used to predict and make the inferences on the SVF, and it records bounding boxes of its predictions, and then this is just like, this is not geospatial, even though it's a TIFF, it's not geospatially aware. So we have translated the pixel coordinates of where these bounding boxes in the notebook to coordinates in the coordinate system that we're using, 6543. But you can kind of see what is going on, and it gives you, YOLO will give you the confidence interval that it thinks this prediction was. So we've got 95 or 91 and 85 are the confidence intervals on that. And we've captured that here. Likewise, you can go in and we can select the layer and I don't know if this is going to be visible. If I make that a little bigger. So this is the 90% confidence building, and this is the 85 confidence building. So we're basically just capturing that information from the YOLO model and translating that as an attribute in the geospatial model. All right, so that's it on the inferences. Let's go and make some point cloud data. All right. So I'm going to close out this one. Save that. The reference data is still working, so we'll just let that run in number 1. So we're going to do colorization next. So this is LAS reprojection. So the data from the NOAA site is not in the same coordinate system, of course, as the DEMs that you download. So this will handle that. It'll do a reprojection with PDAL. So I'm going to load, and there's a PDAL colorization Python that we wrote at the end that basically records the PDAL pipeline, and I'll open that up and we can look at it too when we start to make the data. Once again, we're specifying, hey, our input folder's the LPC, our output folder is going to be this LPC color, but we're going to do some things. Okay, so we have our mosaic DEM, we call it the OPR. We're going to filter points using that DEM. So this will do analysis and say for every cell, do an analysis, and if there's a point that is 50 feet below the DEM surface or 300 feet above, it's probably noise, and we don't want to see it. So it'll filter those points out. And then we're referencing the NAPE file. That's the raster. We want to say, hey, our points don't have any colors. So while you're doing this reprojection, assign RGB values. And this is the NATE file, or this is the TIFF that we want you to get those RGB files from. And we specify the output coordinate system, so we want the data to be US feet, state plane, that's 6543. And then 6360, the data is in meters. So that's just saying, hey, let's make this data consistent in units, both horizontal and vertical. And PDAL will do that for us. So there we go. We've set those parameters. This is where multiprocessing really comes to play. So now we're starting to really get some big data, right? And we, for 30 tiles, it's not going to take us too long, about a minute to do this. So let's go ahead and get that started. So this is going to start to generate the reprojected colorized data. If we go look at the, let me see if I can find this colorization file. Okay, so this actually is the Python or the pipeline, JSON pipeline that we're using. So we're using a filters reproject. It's substituting the coordinate system we gave it in the definition. Then it's saying, hey, we want you to filter out low noise, which are 7 as a classification, and high noise, 18. Then we're going to filter with the DEM using the raster that we defined. The envelope is going to be 50 and 300. And we are going to do a colorization filter. The raster is going to be the NATE file. And then we're going to output the point cloud with the file name that is in the list. Okay, so fairly straightforward pipeline. This takes about 5 minutes. Maybe while that's cooking, let me just show you real quickly. This is the full statewide phase 3 data set. And you haven't used Poetry and Entwine point tiles before. This is my favorite tool. So all you need, this is the pan and orbit, it's first one. And so once you do that, left mouse kind of gives you control to move that data around. Right mouse, you can basically orbit, and then you can zoom with your scroll wheel. On my Mac, the scroll wheel is not the best, but it works. And so we can zoom in, and now, you know, this is what we're making on the machine right now for those 30 tiles. And you can see that we've got much more meaningful information. One thing to note too, if you haven't increased your point budget, sometimes this can help how many, 10 million points to load into your browser for display can make this helpful. But now you've got more meaningful information. This really helps both our clients as well as our engineers that may not be used to looking at LiDAR intensity. If you go to the USGS Entwine website, those are all displaying by default as great intensity gradient, I think. And so not everybody is trained to really recognize or understand. It makes sense what you're looking at, but as humans, we're used to RGB imagery, and so this I think is really helpful for people just as an interpretive product. All right, let's go see if this is still cooking. No, I think if colorization is done. So 1 minute, 1.82 when I ran it before, 1.5 or 1 minute 56, like almost 2 minutes. So not bad. So we're done with this one. And we'll go back and we'll go to the next one. You notice I don't have a 6 in the main list. The 6 can be found inside of the EPT config folder. So that is here. So we're just going to load that one. And when we go to the top, so this makes the point cloud format that you can, that's web enabled and web readable. So this is again a Hobu PDAL project. We're going to load the library there. One thing to know, and I just bring this up mainly for Windows users because we're going to make EPTs from all of those colorized point clouds. And at the end, and we're gonna split them even further to make it more multi-process friendly. Because this is only 30 points, you wouldn't necessarily have to do that normally, but when you do it at scale or big projects, splitting the point cloud data set job into more parts is more friendly for multi-processing type workflows. So this command we're gonna run at the end, and it basically just defines, okay, where does the Entwine point cloud live on your system? What's your temp directory? If you're on Windows and you don't have a temp folder, you can edit that and just change, you can find the merge file in this directly. So, and you could just edit that. You could put it in your temp folder, or you could just take out TMP altogether and then put 2 dots to make it relative to wherever you are. But just a caveat in case you want to run that on the Windows side. On Mac, it's not going to be an issue. We created a little Python file that creates the JSONs. This just gives you the syntax. Again, like everything else, an input folder. Where do you want the JSONs to be? And where's the output folder of the Entwine point cloud data set? So that's what we're going to define in this next cell. We're going to run that. It's going to say, hey, input is the LPC color. We want the output just to be right here in this directory. And then this is going to be the name of our Entwine point cloud output format. So we run that just to set those parameters. There's a make subset command. There's 64 subsets that we're going to run. They're basically Entwine commands. Entwine build a point cloud with this definition. We just created those definition files. They're on my local. They specify the input output, and then which file, which JSON, which subset. So this is one of 64. And that's what we're going to submit next to the, let me close this. So we're going to define that input that has the 64 pieces, and then we're going to run the multi-process pool to execute all of those Entwine commands. This takes, I think I have a table here. This is like a 5-minute process to make all those. Maybe while I'm running that, we can go back here and see if we've got, go back to the workshop main and the reference. And so you can see that my notebook number 1 finally made an RGB file from the National NAIP source. So the National NAIP, it's not Google imagery, but you can see that it's also not got the buildings present here because it is more contemporaneous to the Google.
2022.
Is that what?
For North Carolina, that was they're still working on the 2024.
Okay, so these buildings were removed at some point between 2015 when they were in the 2015 LiDAR, and so in the last 10 years they've gone away. But I just show this just because it's a nice way, and if you have like an irregular polygon, you can still use that with the same command. You just give it a different polygon and it'll clip off the NAIP whatever shape you want. And so it's I think a pretty handy tool. All right, so maybe while that's going, let's look and see. I don't know if that I should run the GRASS yet. Wait, one thing I didn't show you that I think is worth knowing. If you work with Entwine point clouds, so we're still looking at the full data set here. There's a resource at the end that you can grab, and so I'm just going to copy. That may be hard to see, but there's a second HTTP string that I'm gonna copy. And this is basically what is allowing, I'll move that down a little bit, the point cloud to be interpreted. Now, one thing you need to do is add an ept.json to that. And now, through your web browser, you can get metadata on any of the EPT point clouds that you're looking at. So all those that are at USGS Entwine.io, you can just grab the HTTP string, add the EPT JSON at the end. And what this is really handy for is this count. Let me see if I can add that. So it gives you bounding information of the point cloud, but I think what we find most useful is, and what a lot of people ask us is, how many points is that? So how many points? We're dealing with 143 billion points over that 10,000 square mile chunk of North Carolina. That is what I think is super amazing about this delivery device. You can deliver that much data over a web site that's living on servers in Albuquerque and here anywhere in the world. We can access that data and work with it. So that's, I think, a handy tip to notice. The other thing, I think, since I have that on my clipboard, I'll just go here. And we've been involved in a lot of crowdfunding campaigns with QGIS. One of them principally has been to add point cloud functionality to QGIS. And so I'll show you, if you haven't added EPT data to QGIS, all you have to do is go here to the data manager. There's the point cloud, and you can drop that same URL that I used to look at the point count. You can use that here. In fact, that's how you do it. And then you also need to add the EPT JSON extension. So we can add that. And what do you know? We can grab that same resource from Albuquerque and load it. And okay, I know we're zoomed in here, but let's zoom out. That's the full extent, 143 billion points in QGIS. So this, I think, is very meaningful and really, I think, a step forward for data access, not only just via the web with the EPT, but also through QGIS. QGIS also has some really, I think, useful tools that have been added with that. So we'll go back to this data set. Let me turn off some of these other things. So we just kind of look at the point cloud data in the buildings. I'm gonna turn the buildings off here. I'm gonna try to see if I can, this is a little less robust on the Mac, but there's an elevation profile tool. And I have the building layer and my point cloud layer. So this is a profile tool that the idea is that you should be able to cut a profile across something. And then, yeah, so you saw it momentarily. I think there's something with the programming on the Mac where it doesn't maintain the display there. But on Windows, this works really well. And so, but even though that doesn't work, you still have access to all the same attributes that you have with the EPT point cloud. So we have the RGB data. You can use a QGIS query tool, and you can look at, you have to get on the layer, and then you can look at grabbing the points, and you can see it like grabs a cluster of points here, and here's the values. I don't know if that'll be readable, but you have all of you have GPS time, or the RGB, since we added the intensity values, But probably more importantly are the elevation values, so X, Y, Z, and you can just pull the attribution information directly here in QGIS. So that's something to really show. I think I hear my processor die down, so I think that's a sign that we have an EPT. I'm just gonna merge them. So this next command runs the Entwine merge command, puts all 64 together in one. This is a GDAL command to get the coordinate reference system. So I'm just outputting coordinate reference system 6543 to a text file. We can open up that text file. I think it's put it in the EPT folder. And so let's see, date modified. So here it is. I'm going to open that with VS Code. And I'm going to change my view to word wrap. And I'm going to copy this. Okay. And then I'm going to go back to this browser folder. We should have an Entwine point cloud. This has all that information that's served off the web. There's an EPT JSON that we were looking at on the web. I'm going to modify this. And so at the bottom, it tells you what the coordinate system is. So this is a compound coordinate system, horizontal and vertical. I was like, your machine's doing some work. Congratulations. We're actually using it. So we're going to, I'm going to replace this compound coordinate system with just the horizontal only. I'm going to save that. So I'm going to save that and then get out of my JSON. I don't need this anymore. Then the next markdown cell basically shows you how to install the HTTP server locally. So I'm going to grab this command, go to my terminal, and we're going to run that. Might already have that installed here. So looks like it's finished. Once you have the HTTP server installed, you can launch it with the next command. So that's this one. I only put this in, these commands work well. I could put code commands in Mac. I couldn't figure out how to do that for Windows. So, but it still works on Windows if you go to your environment and run these. So I'm going to start the server. Okay. Now I have a local server running, so we can do exactly what we were doing from the Poetry server that lives in Albuquerque, but now I have a local host server. One thing I need to do, I don't know if something changed security on Safari, but it's still viable on Firefox. So we can copy that link and paste it here in Firefox. And now we have the 30 tiles reprojected, colorized, mosaicked, and turned into an EPT that has the same functionality that the 143 billion point data set has. So we can zoom around and we can have the same zoom functionality. These are those buildings. And you've got a really, I think, robust and meaningful data set. There's a lot of tools in Poetry that I won't really go over, but you can pull, this is what I love about Poetry is that you are working with the atomic unit of the point cloud. So you have access to all the points in this application. And so we can run that and you can see the scan lines. So there's multiple scan lines coming across these buildings from different flight lines. And so you just have a super robust data set, you have access. So we can drop that on the field if we wanted to get an elevation value. There's that elevation value, it stores it there. We can look at all the attributes. By default, you've got RGB, but we can do what is commonly done on the USGS website. We can look at it as intensity gradient, so strength of return. You can dynamically, if you want to dial in something a little differently, this is a nice way to view the data. So, and because we have that on our file system, we can go back and we can actually load this. You saw there's two options for point cloud. Hey, I've got this on my local system, and let's see, I'm gonna go to my workshop and I need to find the Entwine folder. So here's my Entwine folder. That's what we outputted. It knows that I want to load an EPT JSON, so we select that guy, and then we just add it. And same kind of thing, so we'll turn off. So you don't really see any difference there. I turned off the full point cloud, and we can zoom to fit and see what we just made with the EPT. So again, that's something we do all the time, every point cloud, because it's really a quality issue for us. If we get thousands of square miles, how do we know what we got? This is one of the best ways that we know, visually looking at, from a quality perspective, what was the airborne collection like? All right, I know we're pushed for time here. Want to do some GRASS work here for a couple more minutes?
5 minutes.
Okay, let me see. Let's see what we can do. All right. So I'll save that one. All right, let's go to the GRASS one. Here, I'm going to start GRASS. Hopefully I've got everything ready on this. I'm going to fire up GRASS 8.4. I'm going to go to the top here. Okay, so again, I mentioned meaning to the point cloud data, the DEMs that we have. We're going to run flow lines with this one. And I think I should have a GRASS terminal. So there's my GRASS data. It's loaded up a temp workspace. I'm going to change directories here to the location of our workshop. All right. And then now I'm just going to run Jupyter Notebook. Okay, and GRASS launches the notebook. Let's see if I can make this. You could run this notebook from the browser. I really like to run it from the kernel. I think we may be done now with number one, so I'm going to close that. Number one. And now let's select the kernel. I'm going to try to select another kernel. We're going to select the Jupyter server. When GRASS started up, it gave me some optional kernels. I'm going to copy this 127 one, and I'm going to paste it in here. There it is. Enter, and then it prompts me for the Python 3. Okay. So now I have a kernel, a Jupyter Notebook kernel, but I'm running it through VS Code. All right. And I'm going to do some just housekeeping environment checking on my system. This harkens back to number one. So you can run a magic command in Jupyter, the %% bash, and then the bash command, in this case pwd, get your working directory, or you can do bang pwd, also get the same thing. And you can run the echo cd on Windows. These pwd commands will not work on Windows. Why? Because now we're in a different kernel that doesn't have M2 base, okay? And so, but Echo CD on Windows will work and print your current working directory. All right, now we're gonna go, again, we don't have the ls command, so we've simulated the ls command here. And then we're gonna write the contents. We're doing functionality for ls here with Python. Next, what I like to do with GRASS, when I set up a GRASS project, I set it up so that the location has the coordinate system of the data we're gonna work with. So I'm just gonna check one of these DEM files with GDAL info to look at, and it's North Carolina State Plain. You can see here, it does have a size, these files of 1600 by 1600 pixels, FYI on the ultralytic side. And then if we scroll down, it'll give me the EPSG code. I might have to, I don't know where that, yeah. So here's the EPSG code on that. It's 6543 from NOAA. So that's what I'm gonna use to set up this GRASS system. On Mac, I don't wanna call Windows BAT. So I'm gonna comment that one out and we're gonna run this one. So there we go. We've created our GRASS project site. Now with the next one, we're gonna invoke that project, okay? So that's all this is doing. And then it gives you some feedback that we've initialized our session. This is kind of where the database lives, the location. And then it's always a good thing to check because if you start to do some work and you've built a website, sometimes you'll try to load some data or you built a raster data and you come to find out that your region is set to 1 pixel. And so that's something that we'll be definitely changing. This is another check for the, this is another check to look at the GIS environment. That shows the North Carolina projection, US survey feet. Now we're ready to import some data. So we import our mosaic of 30 tiles here with GRASS, or that import. Now, next we're going to run some lists on those data. So here we're setting the region to that data set and then running the OPR G.list. One thing you'll notice here, I have to interrupt that because the G.list command is expecting maybe a queue or something. So you can just hit the stop button there. Again, we're going to set the region to that file. And then you can see the dimensions. They made it 1 meter data. Man, this is just, I love this in GRASS, the ability to get visual feedback in your notebook. So here we're just printing that map and you can see the drainage is there. Then we're gonna do an import. There's a reference file that has the quads we're gonna work with. So that just imports the quads. And this just shows the map again with quads on top. And then we're going to use DB columns to kind of look at the attribution. We're going to make a mask for every quad that we have based on the cell name. So the cell name is the quadrangle name. Here we're working with 3.5 minute quadrangles. And so we're going to output those attributes to a text file that's records all of those. We're going to do some substitution on that text file to put underscores in the names instead of spaces that was in the attribution. And then now we have a Pythonized means to go through, cycle through, basically do a for loop with this make quad extract and make a mask and a vector file of each of those bounds in GRASS. And so we'll run that. The above one is just the bash instance. I included that too, in any case anybody wants to look at the bash analog for that. So that's done. Now we can list our vector maps, and we've got some masks here. Again, I've got to stop that command. All right. You wouldn't necessarily have to do that step, but that's what we do if we're going to scale this up to thousands of square miles. We iterate for memory requirements on a machine, typically at the 7.5 minute scale. Just to give us something standard to work with. So here I'm setting the region to that. Now, when we do hydro analysis, we typically want to go beyond the bounds of the map unit, because a drainage basin can go, and we don't know where it's going to go until we do the analysis. So we expand the region. In this case, I'm telling you that we're doing it 600 feet. I like to go even bigger if I can, just because of having good confidence that when we bring different tiles or different maps together, we have a clean edge match on that basin analysis. Now we're ready to do the hydro flow analysis. So we like to use RDOT watershed to make the flow accumulation. Let me click on that and run that. But I was telling Vašek, I'm excited about Dr. Cho's implementation of RDOT flow accumulation. That's an add-on, right, currently. And so, and he's doing some really interesting memory management, I think, to enable larger scale flow accumulation. And that's the #1 input into this type of flow line modeling. And so I'm hopeful that that will enable larger data sets. And so I think that'll be really great to try that out.
Watershed got expanded in its size. It could do an 8.4 as well.
Yeah, it seems like it's able to do more. We've done much larger watersheds than when we started off doing this in 2014. But we still tend to do it on the quad basis. All right, now I pushed it out 100 feet. I'm going to bring it back 100 feet. Sometimes, like you mentioned about edge effect, you get garbage on the analysis. So now we'll still have a 500-foot buffer. And this is, I think, a really huge, important thing. Most GIS don't really conceive, I don't think, of buffering like this using raster bounds. And that's what I love about the computational region. You don't have to do this with a vector, a buffer, a vector. No, I love it here on the raster analysis. All right, so now I'm going to output the flow accumulation model that we made with RDOT watershed. It's going to make some overviews, so that's done. I'm going to start to extract now using that flow accumulation in RDOT stream.extract. And then we're going to run the add-on RDOT stream order. That's what we use to actually extract the vectors, okay? So I don't know if the stream extractions, this shouldn't take too long. It's on the searching now, so it's almost done. Maybe one thing while that's going, we'll load in our flow accumulation. So I need to get into the reference folder. And here's the accumulation map. So for those of you working in QGIS, you'll know that, that's not real meaningful, right? I much prefer the GRASS color table. Well, I included the GRASS color table. And so we can load that and make it a pseudo color map and load the GRASS color table. Let's see, make sure I'm in the right workspace. And here's a Coleridge Southeast ACC linear. So this is actually a text file I created that emulates the GRASS color table for the flow accumulation map. And we can say, okay, yeah, I'm more in my comfort zone in QGIS. And so we can come into those buildings. Actually, let me move those below the buildings. And so we have our flow accumulation in the context of our other data here in QGIS, or even our point cloud data. All right, so let's get back here. Looks like we're done with the stream extraction. So if you run this and you already have it installed, it just gives you the help. So now I'm gonna go, I don't need to do the load the extension, but we do want to run the stream ordering. This to me is huge value add to get the stream network intelligence. We typically use the Strahler, but if you look at this command, it does everything. It adds all the available stream ordering network paradigms. And so, so that's finished. Now that we have that, we always generalize with the snakes when we do our stream order network. This just prettifies the data, makes it from raster delineated to smooth vectors. All right, and now we're ready to export the database. I typically use an SQLite export, and so that's what we'll do here. And then we can load that into QGIS, and I can show you what we've got as a flow network. It's quite a few features, so it's fairly dense. The next steps that I have are basically running an interactive map. We can skip over that. We'll just load up the network, into QGIS. And so there's my smooth ordered line network. And so I'm gonna add that, and let me zoom to layer so you can kind of see that. And put it above or I'll just turn off the EPT. So there you got the stream ordered network, right? Maybe a couple of things that just to show you what I like to do. We have it displayed as a single symbol vector. My preference is to go categorized. So doing some attribution-based symbology in QGIS, we're going to use the Strahler stream ordering. And I like to, since this is water, I like to use the blues, okay? So we're going to apply that. And maybe I'll move this over. So now you can see different colors potentially, but it's still kind of light, and I know I need to zoom in. So what I'm going to do next that I think is super handy is we're going to change the width. You have an option in QGIS for width. Right now the default is set to 0.26. We like to edit that. And then you have access to the attributes here, right? So, not stream. I want to get the Strahler, okay? So we can add the Strahler, and I'm going to multiply the Strahler times 0.1, okay? And okay, and then let's apply that. I don't know, did you notice a change there? So now we've got attribution-based symbology and portrayal-based attribution assisting us to see what that network really looks like with that Strahler attribute. If that's not good enough for you, you can always come back and say, man, I'd like to see that a little thicker. And this isn't really anything quantitatively meaningful. Strahler times a value doesn't make sense, other than the fact that it tells QGIS that, hey, I want, certain attributes to be thicker than others. And since it's integer-based data, it works really well in this kind of an application. So we can apply 0.25 and really see even kind of more accentuation of that. So that is the Coleridge quad. This is the implementation of that in the Navajo Nation, about 2,000 square miles. And I'm going to change the layer visibility. So I have this to scale dependency. to be visible. It is super slow if we don't do kind of attribution-based symbology. This has 50 million flow line features in this data set that we delivered. This was an Army Corps of Engineers project. You can see it's starting to paint in. I'll put the, well, I can leave the attribution-based symbology off and we can zoom in. The other thing that we do, you notice that the data is painting in kind of in a square mode. So we basically take a tiling scheme. It might be like this 16 by 1600 tiling scheme vector. And we tell the network, once we've matched all the quads, that we want a node at every intersection of a stream with a tile. And that helps the display rendering go much quicker so that you can then zoom in very quickly to any, and we do that too. This has also got 1 foot contours displayed here. And so there's a tremendous amount of data there. And I think we better wrap it up there. We're 15 minutes over. But thanks for everybody joining me. I hope it was valuable learning. And if you have any questions, y'all are welcome to reach out to me and we follow up.
Let's give Rob a round of applause. There are refreshments down the hall in 414. Please stop by and grab some.
All right, bye, folks. Online. Stop sharing it down.